Hi there, I am Ben Wagoner. I'm a principal video specialist on Amazon Prime Video and also Western Region Governor for SMPTE. And today we are doing compression techniques and implementations. We'll be talking about 3 new papers on the video compression space that range from new codec technologies to how to enhance existing technologies to take better advantage of them. It's always a dynamic world in codecs, and 2019 and 2020 are particularly interesting years as we, after kind of a nice long period of stability, we have a lot of new codecs hitting the market with a lot of complex business impacts and technical issues, all that kind of stuff. So things are really, really exciting for the codec nerd right now. So let's jump into it. Let's start with Jean-Baptiste Laurent has been working in image processing and video compression for over a decade. Currently is Director of Marketing at Intopix. He is involved in standards groups and industries, focusing on emerging technologies to manage more pixels, save cost and power, and improve quality without extra latency. Jean-Baptiste?
Thank you. Good morning. So today I will introduce you to JPEG XS and how it can help to create bandwidth efficient workflow with ST2110 standard. So as you know, SMPTE ST2110 is taking off. You have many implementation running today. It's designed to be the infrastructure of choice for live production. Going to IP brings many benefits, reducing complexity. You have less cables, it's bidirectional. It's increased agility also, rerouting, easy reconfiguration. It takes less space. It's simplified workflows. You can use smaller buildings, smaller hobby. But it's also expected to be lowering costs with also less cables, COTS equipment, and lower bandwidth. And we'll address this last point, the lower bandwidth. We know that we have today more and more pixels to manage, to store, to transport. But in many cases, the routes are jammed already. So how do we manage the bandwidth? So if we look at today's first SMPTE ST2110 implementation, they rely on the -20 for uncompressed video essence transport. So an HD 60p stream is typically 2.4 gigabits per second per stream. So you will need at least a 10 gigabit Ethernet infrastructure. You will use a COTS IP switch supporting 10 gigabit ports. And if you look at like a simple Ethernet cables, you will use Cat6 cables typically. For replay storage, you will need some intra-frame compression to have an easy read-write access to disk. In HD, it's feasible to do that at uncompressed level, but it's a challenge at cost level and bandwidth. You have already many solutions for the IP monitoring that can manage multiple streams, downscaling, and everything. If you start to look at 4K, then you need to start to look at more than 10 gigabit Ethernet because a -20 uncompressed video essence is typically 9.6 gigabits per second per stream. So you will look at 25 gig capability, 100 gig capability, or 400 gig COTS IP switch. And if you start to look beyond 4K at 8K level, you know that when you start to look at 8K, you don't just look at 60 frames per second, but you start also to look at 120 frames per second per stream. And your stream in uncompressed can be 38.4 gigabits per second at 60 frames per second, but also in 8K, 120 frames per second, it could go up to 76.8 gigabits per second, which is a lot. So what we would call a COTS IP switch has to be able to support 100, 400 gigabits. A single port for a stream is a 100 gigabit capable port. It's a big challenge for uncompressed. You need new scaling capability for monitoring as well. That's what we want to look at. So what if a light technology could help? And that's where JPEG XS start to be of interest, or to easily manage more pixels over limited bandwidth and while safeguarding the low latency and a pixel perfect quality. So when we look at all the codecs that are existing today, within the JPEG committee, when we start to the call for proposal to create a new compression standard, we took a new approach. That approach was first focusing on the latency as a primary value, on the complexity as a primary value, and on the quality. And finally, the group looked at what are we able to achieve in terms of bandwidth efficiency. So that's what's making JPEG XS different from other intra-frame codec and distribution codec. So if you look at the slide here, you can see that the JPEG XS is really focusing in areas where traditional codecs were not looking at least at that level. Also, an important thing was to create a codec that would be agnostic, let's say, to the platform, the hardware platform in which you would implement it. So, in a nutshell, JPEG XS is for managing more pixels, saving cost and power, preserve quality with no latency, and in this context of use, simplify the ST2110 connectivity. So the main benefits are a visually lossless quality, a constant quality across multiple generations of encoding. As you know, in a production workflow, from the capture to the delivery, we will go into many steps, so we need to make sure that the technology will preserve the quality. We need to make sure also that if that technology is used, that it will be low cost in hardware implementation because it's part of the interface, that it will be multi-platform, no latency, so meaning here few lines of pixel, and scalable to address all the formats that we have in our industry. And finally, what is the most important for the broadcast industry, to have open specifications that bring also interoperability in the workflow. So about the quality, so what we did to create the technology is we apply a new methodology for quality assessment that is an ISO standard called a method for near lossless quality assessment on both natural and synthetic image. So which it consists on taking a content and compressing one side and the other side keeping it uncompressed, but the compressed side we will interleave it with uncompressed version. So this is a flicker test. And what we observe in the group with the JPEG XS technology is on the selected set of content that was a mix of natural and synthetic images, is that going down to 3 bit per pixel in compression, which is 10:1 compression if you consider 444 10-bit video source, that the users were not able to distinguish the difference between uncompressed content and compressed content. So we asked the user to identify which side was the compressed one, and down to 3 bit per pixel, we had a, let's say, a positive result. People were not able to distinguish the difference. But if you start to remove that flicker test and you do side by side, as we used to do, one side is compressed, another side is uncompressed, so a less demanding test, we know that on natural and broadcast media type of content, we can push it harder and people are not able to distinguish also the difference. We did show that at various trade shows already, but pushing it down to 1.5 bit per pixel, so which is for 4K 60, 422, 10-bit stream about 750 megabits, people are not able to distinguish any difference from the uncompressed source. And what is also nice, and this quality observation also, is that when we enter in, let's say, in the lossy world where you have artifact that your eyes can see, is that the degradation is smooth. We lose a level of quality linked to the frequency of the image because the codec is using a wavelet scheme. If the visual distance to the screen is higher, my eyes won't be able to distinguish the difference, or let's say the degradation will be smooth. The technology does not suffer from blocking artifact like you have with a DCT-based codec or macro blocks that start to appear. We have a smooth degradation, a loss of details in the picture. So minimal complexity on all platforms. So the first implementation that were presented at previous trade show by Fraunhofer Institute or Intupix, or both, you had some CPU, GPU, FPGA implementation, were showing that we're able to target really cost-effective equipment. So we mean by that, by Intel processor, not the most demanding for HD or 4K, simple GPU process. We're showing at the last IBC 8K 60 frames per second on a NVIDIA GPU cards in a very low latency implementation. We've been showing FPGA implementation running on low-cost FPGAs as well. So we believe that today it's the, let's say, the smallest codec for FPGA at this level of compression and latency efficiency. And more important also, we don't need any external memory when we implement the JPEG XS standard, which is reducing the bill of material, but also the power consumption. It's bring faster speed than traditional wavelet codecs like a JPEG 2000, also in a CPU and GPU, where because entropy coding is much simpler as well. So it's really offering a best trade-off in terms of cost, power consumption, and quality for such level of latency. And what about latency? So according to the MIT, humans are able to detect a latency only above 13 milliseconds. You have to consider the full production chain. I could, with JPEG XS, as it's only consume few lines per encode and few lines per decode, cascade many encoders, decoders, without never achieving such level of 13 millisecond latency. Of course, in the chain, you have to consider the latency that you have from the sensor acquisition in the camera, the ISP, the streaming, and all the editing step to the delivery. So, but if we consider the latency that we were achieving with traditional intra-frame codec used in a remote production or contribution, in a JPEG 2000 codec, we were achieving about 60 milliseconds with a regular JPEG 2000 codec. So 16 milliseconds. Now we are just a tenth of a millisecond with the new JPEG XS technology. This is a massive improvement for live transmission. So, in addition, because it's used wavelet scheme, the codec also enables some level of scalability that are really useful in a production workflow. So, if I got a code stream encoded from a single code stream, I can decode the full resolution of it, but I can also decode a quarter of resolution or a 16th of resolution. It depends on the profiles. I will speak about that. But basically, when I do that, I gain efficiency. I use less processing, in my workflow, and I preserve the latency as well. So if to give you some example, if I get a 8K XS stream coming in my network, I could decode the 4K resolution of it and the HD resolution of it. So if I consider a multi-viewer application, I can easily build multi-viewer without having the need for complex downscalers, additional FPGA processing or software processing. It's part of the codec. And for transcoding and playout, I could also, from a single production stream, directly output the 8K resolution, the 4K resolution, and the HD resolution, and perhaps transcode the HD resolution to an H.264 format, and the 4K and 8K resolution to an HEVC format. So again, I gain some efficiency from that flexibility. So what about the standard status? So we had a presentation a year ago about the JPEG XS standard here at SMPTE, and I wanted to update you about what happened in the JPEG group. So part 1, which is the core coding system, is now completely published, describing everything to implement the codec. Part 2, which defines the profiles, is also published. Part 3, which defines the file format, the container, the transport formats, is also published. The remaining parts that will be soon published, so you have the part 4, the conformance testing, and the part 5, the reference software. Everything is expected for end of this year or early next year. Apart from what happened at the JPEG group, we work also on other initiatives, such as the carriage over MPEG-2 transport stream. This is under ballot now, so it will be published soon also, and the RTP payload at the IETF that is in one of the last draft versions, so that should be soon also officially it should officially go into a final status. So, and finally, when it's about the SMPTE 2110-22, we work at the SMPTE for the definition of the transport of compressed essence, and this document has also been published in September. So let's dig a little bit into some part. The part 2 defines the profiles. You have 4 profiles today. The most important one for broadcast industry are the main and I. The main difference between these 2 profiles is the main is using group of 2 lines, presynced, we say in a wavelet compression of 2 lines. It brings a little bit less compression efficiency than the I profile that has 2 levels, so group of 4 lines. We have other profiles such as the light or sublight for applications that need as less as possible compression, let's say, and as less as possible complexity. Like you would need to put 12 gig below 10, maybe you can use a light profile. But from what we experience in the broadcast industry, 4:1, 8:1, 10:1 compression are really appealing for such low latency compression technology. So the main and the I profile are the most attractive. The containers, well, I discussed already about the TS, the RTP, the 2110. We just added a new initiative in September, which is the MXF wrapping, also for file-based workflow. You have also image format, the GXS file format, a media type format such as MP4 encapsulation that are defined at ISO. So how do I put this in a 2110 system? It's pretty simple. The XS compressed essence will be transported in a similar way as a -22, an uncompressed. It's just another RTP payload following the same mechanism as session description protocol and all the signaling. What we have in the RTP payload of XS, we will not only carry the code stream itself, but also additional metadata, such as every information needed to characterize the video stream, but also the color, like which type of HDR, which type of frame rates, which type of color sampling. Everything is, of course, carried along with the coded data. So, and is there some limitation? There is no limitation for the compressed stream to be transported over 2110. It supports any resolution. You could go even up to 16K by 16K, up to 16-bit. The signaling for HDR is already foreseen in the part 3, and there is no limitation in frame rate. So what are we speaking in terms of bandwidth? So the codec is line-based. The compression efficiency will be influenced by the width of the lines. We define a range of bit rate for the different video formats. I would say the upper limit is more like this, the 3-bit per pixel limit. So let's say an HD SDI equivalent will be up to 200 megabits, 60p up to 400, 4K up to 1.6 gigabits, 8K up to 6.4. Practically, from what we did demonstrate in the previous months, a 4K 60p 422 link at about 700 megabits is completely fine. We can push it down to 500 megabits in most of the broadcast content. We did present it 8K already, not on a big screen, but on a Dell 8K monitor, doing 8K at 2 gigabits per second with 8K 60p 422 at 2 gigabits per second seems to be perfect in quality. So what does it mean? It means that if I look at the compression range, practically I can fit every broadcast video format below a 10 gigabit Ethernet pipe. And if you consider COTS equipment today, most of the FPGA have an upper limit of 10 gigabit. If you consider the SDI world, 3G SDI has a upper limit of 2.4 gigabits. Cat5e cables can carry up to 2.5 gigabits if you have the right switch. 4K can go below 1 gig. So in LAN, you have a lot of Cat5e cables deployed in buildings today. Most of device and workflow have an upper limit of 1 gigabit. In WAN, we need compression. It's a must, and bandwidth as a cost. We are investigating today 2 possibilities: transporting XS as a VSF TR01 stream, so over an MPEG-2 TS, or transporting that over ST2110 with some adaptation for wide area network. There is a group working on this topic at VSF as well. Some ideas that could be also interesting. Traditionally, replay systems are working with phases. There is a work for 2110 to be adapted to that phases approach. With 180 frames per second, HD, we create 3 phases today. It's like sending 3 2110-20 stream over network. If you compress it by 3 and send it that as a -22, you can send an HD 180 frames per second at the bandwidth of 60 frames per second. By 10, you can send a 600 frames per second at the bandwidth of 60 frames per second as a single video essence in a 2110 workflow. So in summary, JPEG XS enable cost-effective SMPTE 2110 infrastructure. It simplifies the full infrastructure from the interface to the switch, to the read and write to disk, to the access for monitoring, and it enabled to support any video format from HD up to 8K resolution. We think that XS meets all the ST2110 quality requirements. It's constant bitrate, it's low latency, it has a good quality, and very low complexity. It will enable to achieve much more with the ST2110 standard. Thank you very much.
Thank you. Awesome stuff. We've got a few minutes for some questions. Get the line up with the microphone there.
Thomas Edwards with Disney. What are you seeing the difference between the 1 and 2 vertical wavelet decompositions? What's the difference in equivalent bit rates?
That's really when you start to compress a lot. Let's say that you get the benefits. In terms of latency first, in an FPGA, the impact will be you got about 11 lines to encode, 11 lines to decode with the high profile, so the 2 level, while on the main profile you will get maybe 6 lines to encode, 6 lines to decode. I would say this is not really significant in terms of latency because it's 6 lines under like 2,000 lines for 4K, so it's nothing. In complexity in software acceleration, we saw some gain to do main versus high. Honestly, I think the gain is at the encoding side and not really at the decoding side from what I saw, but it depends on implementation. So, and in quality, we saw that it was really helpful for also more pathological content, not really media type of content. Thank you.
Okay, any other questions? I had one. In terms of bit depth, do you see a linear increase in bit rate required going from, say, 10-bit to 16-bit? Or is it more like a distribution codec in that the bit rates are somewhat orthogonal from the bit depth?
I don't have a clear answer on this. I would say well, in the testing, well, we did validation on 8, 10, 12 bits. I think we get more compression efficiency, we speak about bit per pixel compression. So compressing 444 12-bit is 36 bit per pixel. We tested down to 3 bit per pixel, and we did the same with 422 10 bits down to 3 bit per pixel as a limit. We did not, let's say, compare it in the way you're expressing it.
Okay. Well, thank you, Joey.